Like, where was it? We're going from procedure 15 through procedure 22. I was looking for the procedure number. It's 21, procedure 22. So when it says save something for procedure 24, you're not going to save that, right? So that's all the further we're going. And this is just the analytical group 3A, 3B. Now when you look at procedure 15, that's where I was heading. There's an A part and a B part. There it is. Sitting there. I'll have to have the page. There's an A part and a B part, but the B part is just to reduce the volume of the solution. You're going to be adding a lot of reagent as you go through the A part of procedure 15. If you don't start off with a small volume, you're going to end up with 2 test tubes simultaneously while you're doing all the tests. In other words, the test tubes aren't big enough to hold all the solution. So what he does in B is reduce the volume of your solution by putting it in the casserole and just boiling it down a little bit. Don't evaporate the dryness. But you want to get down to 7 or 8 drops, he says. It's not critical. In fact, I guess he says 8 to 10 drops. But you want to be down in a small volume. Now when you get your unknown, what do you know about the unknown? How much is it going to be? I always give you 6 drops of unknown. That's why. So you don't have to do part B for the unknown. When we're doing our general unknown, the general, which is experiment 5, there you will probably come out of experiment 5A, 5C rather, with a lot of liquid. Again, you can boil it down. I'll say more about that when we talk about the general unknown. Okay. So basically, you're going to mix up you're going to calculate your drops as before, put them all in the casserole, boil it down a little bit, and then put everything into the test tube. He says 3 drops, you want to use everything. And I give you 6 drops, you want to use the 6 drops that I give you. First part of procedure 15, you're going to start making it basic with ammonia. You're also adding ammonium chloride. No big change there. And by the way, we do have saturated ammonium chloride and 2 molar ammonium chloride. So you want to use the 2 molar. And you're making a buffer of ammonia and ammonium chloride. That's to control the pH so the right things happen. Okay? In particular, we're trying to not precipitate some of the ions from the later groups that might precipitate as hydroxides if the hydroxide ion concentration is too high. So you're adding 15 molar ammonia. And the key thing here is you're adding it, I'm just going to read it to here, drop-wise. It says drop by drop with constant stirring until the solution is just alkaline. Okay? So it's usually 3 drops, but you're just going to add, and one of the easy tests, you add a drop of the ammonia, it's the 15 molar ammonia, you stir it up, you centrifuge it, you add another drop. If it makes precipitate, you stir it up, centrifuge it, that's the way to do drop-wise, and eventually you get a drop that doesn't make precipitate. Okay, that's drop-wise. And it says you want to add 1 drop excess. That one that you add is the excess. Okay? The one that doesn't make more precipitate is the 1 drop excess 15 molar ammonia. So there's no specific number of drops to get it completely precipitated, but then you add 1 excess drop. Now if you look at the flow chart back at the beginning of the experiment, you'll see that everything, well, not everything. This makes a hydroxide precipitate. The iron 3 hydroxide is going to be a reddish brown color. This is sort of a greenish color. This is a light pink color. This is green color with the hydroxide. The manganese, oops, I'm sorry, we're adding ammonia. These two don't make precipitate with the hydroxides at this stage because they make complex ions. Okay? So these two will make complex ions with the ammonia. This will make a precipitate, this will make a precipitate, this will make a precipitate, this will make a complex ion. We didn't put manganese and nickel in, but nickel. Manganese wouldn't do anything with ammonia either. Okay. That's the first step. You add the excess drop. The net ionic equations are really easy. I'll do aluminum. Notice, if I put these one molecule of ammonia and one molecule of water, what do they make? That people keep asking me about. Makes 3 of those. But we never use that anymore because that's chemistry from the 60s. We're in the 2012s now. Modern chemistry, we don't talk about ammonium hydroxide. We have a lot of bottles around that are labeled ammonium hydroxide. School's celebrating its 85th anniversary, and so what's happening? We bought our bottles 85 years ago, so we still have to use up those old bottles that say ammonium hydroxide. Okay? So anyhow, when you do this, you get in other words, all of these hydroxide precipitates go like that. In other words, this gives you the hydroxide that makes the precipitate, and then the salt that's left is the ammonium compound. So you can do that for each one of those that forms a precipitate, something like, actually, 2 plus. Very simple equations. This is the hexamine cobalt-2 ion, and that's an amber color. Cobalt-3 makes one that's even more amber, and you say, what the heck is amber? And it's a yellow-brown color. So those are the sorts of things when you add the ammonia to the ions. Then, continuing on, he said, note the color, and the reason you want to note the color, I started talking about these precipitates. The iron 3 hydroxide is a reddish brown, the 2 hydroxide is green, aluminum hydroxide is green, white, chromium hydroxide is green. The solutions with the complex ions, amber, nickel with the hexamine is a blue color, zinc makes a complex ion with the ammonia, that's colorless, so obviously you won't see. But you want to look at your solutions because as you're making these precipitates, they'll form in different orders. You'll see different colors. People always say, hey, my partner, I was working with them, they got this color and I got this color. What does it mean? It doesn't really mean anything. You just added different concentrations or you added different rates and different things precipitated out first. When we do the selective precipitation calculation, you always say, this should always come out first, but in actual practice it depends on the local concentrations as the drop hits the liquid, how the precipitate forms, and which one forms first. And lots of times, once the precipitate is formed, it doesn't go over to the more insoluble one automatically. In practice, we do the calculations as if it did, but the lab, things like that don't always happen. Okay. Going back to this at 15A, you're doing 15 molar ammonia. I've got to finish that out. And you're looking at the colors, and somebody said, when should I record things? as you're adding it, you can record what the initial precipitate looks like. If it looks the same all the way through, then you don't have to say much more than that. You can say what the solution looks like. All of these are clues that you look back at when you're trying to decide which things are in your unknown. Look back at your reference ones. Notice the unknown won't have all of these necessarily. Okay, once you finish 15A, you don't take it out of the test tube or anything. You go to 15B. There it is. I'm sorry, not 15B. I want to call it 15A2 because B was just putting it into casserole. So the next part here is where you're going to add the ammonium sulfide. It says 8 to 9 drops of ammonium sulfide. And this is where the fun starts. First of all, the cobalt 2 sulfide is going to be black. Okay, this is black. This would be a tan colorful form. These don't really form sulfides. You don't have to worry about that. But these will form black sulfides also. And even if the hydroxide is there, in this case, as you add the ammonium sulfide, some of the hydroxide precipitate for the irons, the 2 iron hydroxides, do get converted to sulfides. So at that point, you'll have both sulfides of iron and cobalt. Okay? And the other thing that happens, everything's going to turn black in your test tube, even though the nickel is not there. And the unknown is that when you're working with the unknown, it's possibly due to nickel. If you don't get any dark color precipitates at all, that means you don't have some of the things that could give you black precipitates. But what happens is, your test tube looks like that. And you centrifuge it, and it still looks like that. And you centrifuge it some more, and it still looks like that. That's because cobalt sulfide isn't as bad as the nickel sulfide, but when you're doing your unknown, you might potentially have nickel. But the precipitates are forming colloidal particles, and they do not centrifuge out. So what you do is try to break down the colloid by adding things like ammonium acetate. That's the reason the ammonium acetate is 4 molar. I keep saying it's 4 times better, but it's also for this particular procedure because the more concentrated solutions discharge the charges on the surface of the precipitate particles, and they're more likely to coagulate. The 2 things you can do to make them coagulate is heat the test tube and also add some ammonium acetate. Now, one of the things he points out when you try to heat the test tube with the ammonium sulfide, sometimes it bubbles out of the test tube and you have a beaker full of black particles again because of the precipitate bubbling out of the test tube. So all you have to do is be careful there. If it starts getting foaming up to the top, you lift it out of the boiling water bath, right?